Hello everyone, I am Rekha Murthy, Assistant Professor of Department of Electrical and Electronics Engineering from Sai Vidya Institute of Technology. Today I am here to continue with the next session where I am going to explain about the concepts related to the Module 2. The concepts are the directional earth fault relay, impedance relay. So now, and also the distance protection. Okay. So here, let us go through about the directional earth fault relay. So in this case, for the protection against this earth fault or for the protection against the ground faults, only one directional overcurrent relay is required. Okay, and its operating principle as well as the construction is almost of the directional overcurrent relay as what we had discussed earlier. It will be consisting of two elements. One is a directional element and an IDMT element. So a directional element has got two coils. One coil is energized by the current and the other by the voltage. So the current coil of the directional element is energized by the residual current and the potential coil by the residual voltage. So that you can see it here in this diagram. So they will be provided with the current coil and the potential coils. Okay, so this connection which we are going to do, it is suitable only for the place where the neutral point is not available. Okay, if the neutral point of an alternator or a transformer is grounded, then that connections will be done as you can see in this figure. So here, if the neutral point is grounded through the voltage transformer, then the voltage coil of the directional element, directional earth fault relay will be connected to the secondary of the voltage transformer or the potential transformer. So here, usually the IDMT element will be having a certain flux setting of around 20 to 80% of it. So here we can also consider this voltage transformer with having a more number of the limbs, that is a special type of a 5 limbs of a VT which can also energize both the earth fault relay as well as the phase fault relays. Okay, so this is what about the directional earth fault relay, which will be having two coils. One is a current coil and a potential coil, which has been energized by its own parameter, that is the residual current as well as the residual voltage. Okay, so whenever you find there is a fault, the earth fault is going to occur, immediately this relay is going to operate. This directional earth fault relay is going to operate. Okay, now let's move on with the next concept, a new concept, that is a distance protection. Distance protection is widely used. Where do we use this? Widely it is used for the protective scheme for the protection of high and extra high voltage transmission as well as sub-transmission lines. So this scheme is mainly make use of a number of distance relays, which is going to measure the impedance or some components of the line impedance at the relay location. So the measured quantity will be nothing but it will be proportional to that of a line length between the location of the relay and the point where the fault has been occurred. So this measured quantity is directly proportional to that of a distance along the line, and the measuring relay is called to be as a distance relay. Okay, so here the overcurrent relay which you had studied in the previous sessions, they have been found unsuitable for the protection of transmission lines because the drawbacks of variable reach and variable operating time due to the changes in the source impedance and the fault type. So that is why the distance relay has been developed in order to overcome these problems which has been associated with the use of this overcurrent release for the protection of transmission lines. Now, the modern distance release usually provide a very high speed fault clearance. So they are used where the overcurrent release will become very slow, and it is very difficulty in the grading time overcurrent release for the complicated networks. So that is why this distance relay will be employed for the protection of a transmission and sub-transmission lines with the range of 220 kV, 132 kV, 66 kV, and 33 kV. Sometimes they are used at 11 kV. And if you make use of the 132 kV and 220 kV systems, then the recent trend is mainly used to if you have to make use of a carrier current protection. Okay, and usually this type of carrier current protection, usually they operate under the control of a carrier signals. Okay, so here let us consider this distance protection scheme is a non-unit system of a protection, and a single scheme is going to provide you both the primary as well as a backup protection. Now let us see what all the different types are there in the case of the distance protections. One is the impedance release, reactance release, Moore relay, angle impedance release, quadrilateral release, and elliptical and other conic sections release. Now let us go through about one by one. The first one is the impedance relay. So the impedance relay usually measures the importance of the line at the relay location. So whenever the fault is going to occur on the protected line section, the measured impedance is nothing but the impedance of the line section between the relay location and the point of the fault. So whatever the measured quantity you're going to get it from that relay, what are the information you're going to get is nothing but the measuring quantities, right? So that measuring quantity is proportional to that of the length of the line, and hence the distance along the line. Okay, so generally we know that the term impedance can be employed, it can be applied to a resistance alone, a reactance alone, or a combination of the two. But in a distance relaying terminology, the term impedance is going to include both the resistance as well as the reactance. Okay, now let us see what is the operating principle of this of an impedance relay. To realize the characteristic of this impedance relay, the current is compared with the voltage at the relay location. The current is compared with the voltage at the relay location. The current is going to produce a positive torque, that is nothing but operating torque, and the voltage will produce a negative torque, that is called as restraining torque. So the equation for the operating torque of an electromagnetic relay, it can be written as T is equal to K1 into I square minus K2 into V square minus K3. So this equations we had already seen in one of the modules. So we have already proved it. Now this is not a new thing, which already we have proved why this is T is torque equation for the electromagnetic relay, why it is becoming square of it. So since here there is a two parameters which always getting compared, so therefore now we need to take the K1 times of I square, and also we need to take a K2 times of V square. What is this K1, K2, K3? Those are all the constants. Okay, in the previous modules we had discussed torque is directly proportional to that of either I square, or either it is a V square, or either it is a combination of V into I, right? So the proportionality constant is nothing but a K. So here we have taken the individual terms, so therefore there will be a three individual terms, K1, K2, K3. K3 is being the torque mainly due to the control spring effect. So when you're going to neglect that effect of a spring, it will be very small. So the torque equation can be written as T is equal to K1 into I square minus K2 into V square. We are neglecting the K3. Now further, now our aim is we need to find out at what condition this relay is going to operate. What does the condition need to be satisfied? See, this value, the K1 into I square minus K2 into V square is greater than 0. We are making it to be as maximum as possible. So torque is maximum. So when T is greater than 0, do you agree with that? So that is why this value will be greater than 0. When you equate this to be greater than 0, so it results with this simplification, that is K1 into I square is greater than K2 into V square. Also, you can further simplify this in a different way that you can write it here in this way. Now when I take, my interest is I have to find out the impedance value. What should be the impedance value? So here, when you simplify further, when you take the impedance is in ohms, so how do you write it? The ratio of voltage by current. So make it simplify this in such a way that we should get V by I. When you get V by I, you will get it as V square by I square less than K1 by K2, which is nothing but a constant K. So finally, you can say that Z should be less than K. So that is what we got a solution, that in the case of an impedance relay, whenever we employ, we need to take up this expression, which is very important. When does this relay is going to operate? So the relay will operate if the measured impedance Z is less than the given constant. This is a final conclusion. When do you employ the impedance relay? After getting clear with this, then only we can go with the characteristic. So in the characteristic, let me talk. In the characteristic, you will have, just a minute. Okay, also for, if you consider for the any kind of the static or a microprocessor based relays also, there also the I is compared with the V. So for the operation of the relay, here also the following condition need to be satisfied. Similarly here, when you solve, again we get the value Z should be less than K. That is about the, when you realize impedance as a static relay or a microprocessor based relay. Okay, so we need to realize this impedance relay in a 3 different modes. One is electromechanical, then static, and a microprocessor based relays. Okay, so for all these, when you're going to realize it, the condition should be one at the same. That is, Z should be less than K. Now coming to the impedance relay characteristics. So the diagram which you can see here, so this is a characteristic of an impedance relay in terms of the voltage and current. So in case of an electromagnetic relay, the characteristic is slightly bent. It is slightly bent. Okay, near the origin, mainly due to the effect of the control spring. But in the case of a microprocessor based or a static relay, the characteristic will be almost, it is straight line. It will be straight line. Okay, fine. Let us not bother about this, why it is straight or why it is slant or why it is slightly bent. Our aim is we need to find out in what part of a region does your relay is going to be active. Okay, so now here, this let me show the diagram, that is the RX diagram. So the same characteristic I'm going to replicate onto the RX diagram, in which you will find that Z is equal to K. It represents the circle. This Z is equal to K is going to represent a circle. Okay, and Z, when the Z value is less than K, that indicates that area, when the Z value is less than K, that indicates a area is within the circle. So thus, we can say that the zone within the circle is the operating zone of the relay, and its radius is z is equal to k. Okay, so k is equal to the impedance of the line, which is to be protected, and the psi angle which you can see, that is a phase angle between the voltage and current. So as operating characteristics is a circle, right? So the relay operation is quite independent of that of the angle, phase angle psi. But the operation is mainly depending upon to the magnitude value of z. So if a fault point is if the fault point is on the protected section of the line, then it will be lying within the circle. It will be lying within the circle. If suppose you find the fault is here, right? So that means the fault is within the circle. That time the relay should trip. The relay should trip when the fault is occurring within this region. Suppose when the fault is occurring somewhere outside the circle, that means this relay doesn't have any duty to perform. It will not do. It will not perform. So that stage we can call it as a block stage. Block stage. Okay. So make sure whenever the fault point is occurring within the circle, then only the relay is going to operate. So z value is less than k. Okay, so for this condition, the relay will operate and send the tripping signal to the circuit breaker, and whenever the region is outside the circle is the blocking zone. So if the fault point lies in the zone, then it is beyond, indicates that it is beyond the protection section of a line. It indicates it is beyond the protection section of a line when the fault is outside the circle. So the relay will not respond. So in such situation, the fault point may lie in the protected zone of some other relay will be there. So the operating time of this relay is constant with the irrespective of the fault location within the protected section. So this is finally this is a diagram with respect to the distance and the operating time. Also you can observe here, this is the region where it is almost straight, right? So here it indicates this is an operating characteristic. This part of it is indicating about a negative torque region. Negative torque region. So at this region, that means it is under the normal condition. When it is going to go to the positive torque region, means it is going to the relay has to operate. Okay, so this is about the characteristics. Now coming to the directional units. Okay, why do we have to make use of a directional units? What is this directional unit? Okay, see, it is very important from that impedance relay characteristic on the RX diagram that an impedance relay is a non-directional relay. Impedance relay is a non-directional relay. So because as its characteristic is a circle, so the relay will trip for a fault point when it is lying within the circle, irrespective of the fact that the fault point lies either in the forward direction or in the reverse direction, that we don't know. Correct? So that is why we have to make use of a one directional unit. We are not able to identify whether the fault is occurring in the forward direction or in the reverse direction. That is what is challenging in this impedance relay. That is why we are going to make use of a directional unit. So let us go with the directional units, which is used with the impedance relays. Let me show that. Okay, you can just look at here in this diagram. Okay, actually here in the previous diagram in the circle, that is it is always see that a relay should operate for a fault which is lying only in the forward direction. So it should never operate for the fault points which is lying in the reverse direction. So to restrict the tripping zone in the forward direction, only a directional unit is included in the protection scheme. Okay, so at any location, Okay, at any location, I have considered the three zones. At any location, three impedance relays and directional unit has been employed here. So here you can see that this is what the characteristic which you can implement further. This is one zone, the second zone, and this will be the third zone. So along with this, we are going to make use of one directional relay, which is indicating a straight line. So that is indicating about the whether the current is in a forward direction or it is in a reverse direction. Whatever it is, whether the fault has occurred within the circle or outside the circle, then you should know what direction it should be. So that is why we are going to make use of a directional unit. So this directional unit when you're going to use, also you can see that different time periods has been allocated for the each of the zone. And this is the part of the positive torque and this will be the negative torque. That means when the this is under the normal condition, the negative torque will be produced. Under the abnormal condition, the positive torque will be produced. Okay, so that is what the indication of this providing a directional relay. Now let us see that how you can replicate this by making use of the directional unit in the circuit. Okay, so you can make use of this circuit where the directional unit is connected in series with the impedance relay. So a directional unit is nothing but it is a representation of a like a capacitor. That means two lines is with parallel. So it is indicating about just like a capacitor. Okay, so this is in series with the impedance relays. So further you can see the one more connections that indicates if only one measuring unit is employed, then what will be the connection. So this connection part I'm going to discuss in the next session very in detail, but just you look on to this diagram. That's it. This indicates that how you're going to make use of a directional unit in series with the impedance relays. This is the components of an impedance relay which you're going to make use of it when you're considering the three zones Z1, Z2, Z3. And in addition to that Z1, Z2, Z3, what are the additional elements we have to make use of it? That can be observed here. Okay, so very in detail explanation will be given in the next session. But here, what we have to take out the information is the directional unit will be having a straight line characteristic, which you have seen here. And it all allows the impedance relay to see only in the forward direction. So the torque equation of the directional relay is given by T is equal to K times of VI into cos of psi minus alpha. That is psi minus alpha. You neglect, we will neglecting the spring effect. So psi is an angle between the V and I, and alpha is nothing but it is an angle of maximum torque. So for the operation of the relay, now how do you solve this torque? Torque should be positive, right? So let us equate that K times of V into I into cos of psi minus alpha greater than 0. When you solve that, what you will get the answer is psi minus alpha is less than plus or minus 90 degree. That means the directional, this is the operating condition when you consider the three zones with including the directional relay. So directional relay employs two pairs of contacts. One pair is placed in series with the contacts of the impedance relay and the another pair is connected to energize an auxiliary relay. So the contacts of the auxiliary relay, when it is de-energized, short circuit the current coil of the impedance relay. So the contacts of this auxiliary relay will be opened whenever a fault occurs in the forward direction. So this type of control is very much required to avoid the contact race between the impedance relay and a directional relay in interconnected or a double circuit lines. Okay, so I would like to conclude here. So we had discussed about the distance, we had discussed about the fault relay. Okay, that is nothing but a directional earth fault relay and distance protection. In that distance protection, we had discussed about the impedance relay, which is very important. So the impedance relay operating principle and characteristics, along with the RX diagrams and all. And here, now, why do we use the directional units? That and all we had learned from this session. So in the next session, we will discuss very in detail about these two circuits, and as well as what are the protection schemes which you are going to employ with the impedance release. So that we are going to discuss. Thank you for watching this video.